Thanks, Gopal, and thanks everyone for showing up and doing it for the adjusted time zone, which I think is as a result of me having to do something with my child later on this afternoon. That's a regular thing. So, yes, as Gopal said, that's what I'm going to talk about. In particular, well, I'm also summarising what I was doing in Lancaster for my sabbatical. So this is definitely work in progress. It's not finished, so if people want to make any suggestions and say you should be doing this or we have similar problems for this, etc., it would be greatly appreciated. The thing that we're concerned with in this scenario here, as part of this grant, tide, of which there's a few members I've seen turn up here from the Oceans Institute, we're doing a lot of measuring in the ocean and trying to infer in the ocean. One measurement device, particularly that industry, but also scientists, I say particularly industry because I was motivated by an industry question in this one, that they use are these drifters. So you have a measurement device, you plonk it in the ocean and it flows. So the question now is, which is I think a little unique, and if anyone wants to put up their hands and say no it's not, that's fair enough. But in that, if we want to think about a decision theoretic active learning approach, a sort of a Bayesian sequential design if you like, typically they're static. You put a measurement device in a certain spot and it stays there. But these ones don't. They get pushed through the medium. You have measurement devices that are being pushed through a medium, being pushed through a medium that it is actually trying to measure itself. So that, in a funny way, was a little bit of a quirk. So let's get in, and it's a colloquium, so it's going to be very high end. So yeah. So I'll get to it. Otherwise, maybe I won't get. But that's exactly right. They throw it overboard. It takes off according to sort of Lagrangian flow type, ocean structures. So in that sense, times have changed. Okay, since the days when Sir Ronald Fisher, I love that picture. Yeah, so that's in the days when data was really hard to come by. Right? And you can see him really thinking hard over some data set, and he's clinking away. And he's written this excellent book, this is in the 1930s, about how to design experiments, in other words, how to acquire information. And, experimental design since then has undergone a lot of changes, and people may or may not know the sorts of history on it, but other people, Neyman and Pearson started to develop those ideas later on. George Box with response surface methodology, etc. It turned out to be his son-in-law, actually. And but at the same time, in the early 1960s, people started to also think about it under a probabilistic theoretical design approach. Okay, so the people with those sorts of ones were, Rafer and Schlafer released a book in, I think it was 1961. And Dennis Lindley formalised a lot of these ideas in the 1970s, and it's essentially a decision theoretic framework where you're making decisions under uncertainty. Okay? And that's the ideas that we're going to be building upon. And that sort of optimal design, as they like to call it, then really does permit a coherent sequential design strategy. I've got so many points, where do I get the next one? By optimising a utility function. So, I think I'm pretty slow on the uptake because the primary boundary at my residence as a child was the Pacific Ocean, so the biggest ocean that we got, and I didn't have to cross a road or anything, there was just ocean. I've been in and around the ocean all my life since, but it wasn't until I started working with it statistically that I realised just quite how big it is and how difficult it is to get comprehensive measurements. Okay, so it's a scenario, if you look at that, it's a lot. What do they say? It's 70% of the world's, of the Earth. They've got all sorts of little statistics for it. That 90% of it's deep ocean, more than 200 metres or so deep, whatever. That 20% of the seafloor only has been, I don't know how they get these numbers, I just looked up NOAA and they told me these sorts of things. But it's big. And that makes it really quite difficult to measure. But it is important to understand for a number of reasons, okay? And this is just a few to put up some pictures, I suppose. This one here is a map of all the undersea submarine communication cables. There's about 1.5 million kilometres of them, sometimes very, very deep, so that's difficult to get a handle on. There's some guy trying to do some repairs. I presume he's not doing that at a couple of thousand metres, but... And, you know, we want to be able to... We want to get a decent handle on these sorts of things. So, for example, when the Japanese Tohoku, or whatever it was, earthquake occurred, it cracked these lines. Japan lost all contact with the US, Southeast Asia, etc. And of course, there's just basic maintenance to go on. And you can we first started thinking about this problem, actually. That wasn't in so much a temporal sense, but we started looking at it. If you have to do things like this or put remote underwater vehicles down there, could we think of a design strategy that would be advantageous? You get more information for your buck. It's very expensive, all the rest of it. And of course, there's also you know, gas pipelines, oil pipelines. There's about 1 million kilometres of them floating about, and things can go very wrong at times with these sorts of ones. So this was the, you know, the Deepwater Horizon explosion in Mexico. Of course, lots of damage, killed lots of things, spread a lot of oil around, and we'll come back to this one because they then started a really strong drifter program to try and understand where these surface currents were going to be moving all this oil, etc. And of course, there's your basic things are warming up. And what sort of effects does that have on marine diversity or whatever, okay? Those sorts of more environmental aspects of things. And that's not half the reasons you want to go and have a look at the ocean probably, but it's, you know, there's a lot of it and it's hard to measure, but it's important to measure. I got all this from IMOS. Some people out there, I don't know in this audience, know more about IMOS than I. If people ever looking for a comprehensive collection of data with respect to the ocean, IMOS is great. And it's really easy to access. So it's the Integrated Marine Observing Systems Operation, I can't remember. Observing System, yeah. The point of this slide is you can see a lot of things are very expensive. They always seem to be out in the middle of nowhere. They've got big expensive equipment. They're trying to drop it in. You know, they're you know, these are deep water moorings. You know, they're expensive to run. We've done some work around those sorts of ones. They've got these ships of opportunity that go out and about, and the reason they are called apparently ships of opportunity is that it's just all expensive. So people have ships that they say, hey, volunteer our ship for this. They go, beauty, and we'll put on a few measurement devices and off you go. I think that's an Argo float. What they do is sink down to about 1,000 metres, measure currents down there, then sink down and drift along down there, then sink down a bit further to a couple of thousand metres, measure various processes down there, then come back up, report it. They say that's a cheap way of doing things. And of course there's remote sensing, and there's a lot of different things that go off. That's IMOS by numbers. I really recommend it. There's a good PDF document that then I stumbled across that talked about the first 10 years of IMOS, and it's an interesting read actually. I think it was set up in about 2006. So we've got this huge expanse. There's lots of things going on. It's very expensive to get a handle on, but it's very important. And one thing I haven't measured here, well, talked about here, sorry, but I'm going to, is these drifters. So on these occasions, they just throw them overboard and then they skedoodle off, right? Often what they call drogued, this is a drogue apparently, drifter, in other words, the surface current just grabs that and marches it along. So depending on what the ocean's doing around this spot, this measurement device moves. It's quite different to your sort of, you know, Eulerian type of structures that measure how fluid goes past a point, for example. Okay? So they often call these sorts of ones Eulerian and the other ones Lagrangian. The deep water mooring ones are very easy. You know, get a predictive density of the ocean, drop a mooring here, but it costs them heaps, and you give them a point in the middle of nowhere, and they have a point. There is a global drifter program by NOAA, which makes it look like there's heaps going on, but there's actually not that much. But there's stuff out there. I'll keep giving these caveats. We're going to see no real data today. This is all being done. We're just trying to think about what we would do if we've got a situation like this where our measurement device is pushed by the medium that it's trying to measure. So this is in the Gulf of Mexico, and that's where the Deepwater Horizon oil rig was and blew up. And then there's been lots of studies since then, people putting in, this is a paper here, a gridded surface current product for the Gulf of Mexico up from consolidated drifter measurements. The point of this slide is, let's say we want to think about where to drop drifters. In this one here, you know, they've started essentially where this is, okay, where this happened. So they want to know what the currents are doing out from there. But as the years went on, they also put in other things. And so this is another clump, and this is their trajectories over a period of time afterwards. The point being that the placement of the drifters can make a big difference. And they do drift, and as time goes on, these guys will be acquiring new measurements, and we want to be able to think about where we're going to put our next set of drifters before these ones are done potentially. So you're averaging, you're integrating over a whole heap of possible trajectories, if you like. So I should actually just introduce a couple of the collaborators with this one. First is a PhD student, Ray Jang. He's done a lot of the computing for this. The reason I went to, and he's from Lancaster, the reason I went to Lancaster is David and I started bantering these ideas about how hard it was to observe the ocean and what could we do about it. So Dave's a really decision theoretic probabilist. Okay, so, you know, bandits and regrets and reinforcement learning and all those sorts of things that they think about. So, and I've known Dave a long time, and we started bantering these ideas actually a couple of years ago, but we got a bit more formal 6 months ago on my sabbatical. Henry Moss, who was an old student of David's, he's a really good machine learning guy, so a lot of this stuff I'm going to talk about is really big in the machine learning industry these days, okay? And most of you here will know Lachlan, who's an old student and postdoc of mine. He kind of still is a postdoc, but he's about to take off to the UNSW for a lectureship, which is good stuff. They've got a good department. And he's on parental leave at the moment. So anyway, they're the people that have been doing a lot of this work as well with me. And it was mainly these three that I was working with in Lancaster during my sabbatical and a lot of these ideas. So, what are we going to talk through now? We're going to do a little bit on just what decision theory is. Then, to put the ingredients together, we're going to talk a little bit about building surrogate models for unknown processes, unknown functions, if you like, in the form of Gaussian processes. Okay? And I'm sort of assuming most people have a vague idea about that. And then to put it into the context, because it is also a maths and stats colloquium, I'm going to introduce the notion of sort of active learning and design in terms of Bayesian optimization. How do you optimize a function if you don't know the function itself, okay, but you can put a probability distribution over it. Okay, so I think certainly in the maths department people will be interested in that. So, what is decision theory? Well, basically it boils down to that. Okay, that's easy enough. Just pick the best decision. But what does best mean? Well, you have to define all this, okay? You have to define a set of actions. Then you have to assign a function, a utility, that's going to rate those actions, if you like. Okay? That's going to be a function that's going to take those actions and put it onto the real line, so we've got a number for it. So they can either be incredibly simple, but they can also be very complex. But let's see what we go. And then the basic idea is to pick A with the highest or lowest, maximum, minimum, optimum value of your utility function. So that's all well and good. But of course, what we usually don't know really is what the future outcome may be. So something will occur at random, okay, and be realised by this little value x that lives in its own space. Now, if we do know the probability distribution of the outcomes, we have a realised utility, okay, associated with an action that you've chosen and an x that might come in the future. So we don't know it. So if you're playing roulette, you don't know it. You make a $100 bet. You put that down and then you wait to see if you win or not. And in our sense here, the action may be, do you make the bet or not? And most of us will understand that with the casino you don't. They've figured this stuff out pretty well and they know not to do it. So, but what you are then doing really is taking the arg max for A, okay, over the expectation over x with respect to that distribution, okay, because that x inside the utility function now we don't know. And to sort of jump forward a little bit, we're going to be looking at this x as points in space sort of idea, where to put the next spot. In this case, you know, I actually scribbled it down. I swore I'd keep my eyes on these and see if I missed anything, but well past that now. So in this, you know, why do I say, so the possible actions in this would be to bet or not to bet, okay? Now, on those roulette tables, and then we'd want to choose the utility that gives us our best shot. In this one, we're just going to think about it purely as a financial transaction. I'm going to bet $100 on black. Okay, so there's equal amounts of red and black. And if black comes up, you know, I get my $100. If I don't, if it doesn't, if red comes up, I lose the $100. So, I'm hoping that's under that bet, right? You win 100, you lose 100. But does that pay off? Is that in your favour? Is it fair? Is it disadvantageous to you? The answer is it's disadvantageous, right? Because on these roulette tables, they either slip in an extra zero, or and sometimes they slip in 2 zeros. So the probability of you winning your red on that is not 18 on 36, it's 18 on 38. So with an 18 on 38 chance, you'll win $100. And with a 20 on 38 chance, you'll lose $100. And if you take an expectation of that, you end up with, I actually did it, you'll be down $5 on average. $5.26 actually, and just by doing an expectation calculation, okay? So, you know, your two decisions. Do you make the bet? Well, if we do make a bet, that utility, that, you know, say A, don't do it. Well, sorry, A, do it. That expectation is going to be negative $5.26. B, don't do it, you're zero. You're bigger, right? You've optimised your choice in the face of uncertainty. Says, I'm not betting at the casino. They've got it wide. And of course, that's why casinos then reserve the rights if they think you can shrink that uncertainty to kick you out for no reason. They just walk in and say, no, something's going on, off you go, see you later. So that's the basic notion. More formally, furthermore, we usually don't know P of X either. So, we specify some probability model, whatever, with a parameter vector theta, get some data, estimate theta hat, for example, to get P of theta hat. And in a Bayesian sense, what you can do is combine all this down into a posterior. So you have a bunch of observations, and you're doing the same thing. You're getting the expectation over this U here with respect to the posterior distribution of X now that we've observed, okay? And you're taking the arg max over that to get the optimum one. So it's all just the same thing, we just have a posterior distribution down there now. So that's the sort of the main formula. You could have put condition on D and that, but anyway, that says that. So when people, well, I should have pointed out maybe, because I thought I should give you some history. I know it'll be written down under there. Interestingly, so under this scenario here, it's very easy to think about in a frequentist classical sort of sense of probability, okay? And indeed, von Neumann and Morgenstern did those sorts of ideas in this. You could, when our probabilities are objective, a fellow called Jimmy Savage, who unfortunately died way too young, in the 50s, etc., he thought about this in subjective terms and took a Bayesian route on it, but they both come down to the same conclusion, that basically, if you assume that a rational decision maker will choose the best action with respect to this utility, you're good. Okay, you're fine. So obviously I'm going to be living in the Bayesian world with this, so I don't have that scenario, but you could very easily do that in this case. Okay, so that's decision theory. Now, let's say it's not quite as, I'm going to start to embed this in a Bayesian optimization problem. Okay? Say we have a function and we want the max. We want the maximum value. We want to try and go for some peak. It's kind of looking like that one there. And so what could we do? Imagine this is a computer model that you, in engineering or whatever, you pump out your computer model, it's intractable in the background, and you know, you don't have gradients for it and all this sort of stuff. What could you do? Well, this is the true f. And I'm just going to assume that this f is going to, my belief about that f is going to be represented by a Gaussian process model, okay? Which is essentially a stochastic process with a zero mean and a covariance kernel that basically tells us, under some function or another, that points closer together on the input space will induce higher correlation to the points on the output space. That's a Gaussian process. There's a few other details, but which a bunch of you will go, yeah, we know all that, and I'm not sure if it'll give much more. But essentially, if we generate from this Gaussian process, we'll get lots of wiggly lines that pretend it's a function. But then we observe some points. And so we collect some initial data, fit our Gaussian process, so you see it's all being pinched at the points where we've observed it. In other words, this is a deterministic function. So I'm using a random process to describe my belief about a deterministic function, which means that once I've observed the value of that function was cos x or something or other, yeah, that point x, I know it exactly. So the standard deviations collapse. There's no uncertainty at the actual points, but in between there is these wider intervals. And you know, what we could do then is we fit a model, we have a look at it. No, we're going to need more data, so we chuck some more points in there, we refit that. This is just doing it randomly. Okay, so we've got no, that's really, you know, that's a broad church utility function, if you like. And then you'll do it until, in some sense, you're happy. You know, you've got 30 points, 20 points, 10 points, etc. What does happy mean? All that sort of stuff. That's a good point. But what you do see is, as you start to fit more points, these uncertainty bounds start to clamp up, and we get a better representation of the function. Indeed, at the end, after 30 points, randomly sampled, you know, that mean function of ours, it's actually probably quite hard to see. There's a light blue line going through here. So at this point, you know, we're kind of out, but we also know we've got a lot of uncertainty, etc. You should be going out a bit because, you know, their intervals according to probably a 0.95 probability interval. But as you start to tighten it, these start to change. So the blue line there is just underneath it here. It hasn't got right up. You know, it's shooting up hard that way, and this side's shooting up hard that way. They both want to go up, but they don't know how far to go up. The point is we start to learn more about the model. At some point we stop. Yeah, and in theory you could do that and finally go, once you're satisfied with all those uncertainty, you know, I've identified that as the maximum, and I haven't needed the function to do so. I haven't needed gradients, I haven't needed any of that to do it. But we could do something a little more sensible. And this is getting to the start of the crux of what we're really talking about, Bayesian active learning for optimisation. You do the same thing. You got a function, fit a bunch of points, get a surrogate model. So you have a distribution, you have a posterior distribution over all the points of this function that are not observed. So that's the first stage. And you can see what I'm going to get to on this. On the second stage, so they do this a lot in analysis of computer experiments as well. Could I construct a utility function that helps me search that space better? Effectively what they're going to ask for, what a lot of people will state is, you want a utility function that searches this space and takes into account global as well as local behaviour. Their claim is that it is globally, it's a global option. We can talk about that, I'm not sure if I buy it, but it works pretty well. So, what do we mean by that? Let's let, so far, F star here, okay, is the best one that we've got. That's the highest point on that line that we've fitted here. Okay, that's F star. Now, utility functions, you often don't see them written like this in Bayesian optimisation, but they are just these utility functions like I talked about beforehand. The utility functions for Bayesian optimisation tend to be based on this exploration, what they say, versus exploitation strategy policy. That, you know, there's a lot of names. Machine learners are overtaking this and redefining everything as well and that sort of thing, but it's all good, it's the same ideas. So, what do they mean? Now, there's a lot of different acquisition functions. This one here, which I'm going to show, is what they call expected improvement, okay? And that was, you know, this stuff, this sort of idea was done originally in the 1960s. What was his name? I've got it written down. Kushner. And he was considering this problem for when you were trying to find an optimum for a function with noisy realizations. That's what he was trying to do. In 1998, a fellow called Jones and others published work on this in it's a Journal of Global Optimization, I think, in 1998. And they employ this strategy, claim it's global, maybe, you know, not global in the way numeric analysis would think about things, put it that way. I'll try and explain what they mean by that. But the point is, they construct this expectation. So this expectation here, if you have a value at F star, we're going to choose our next X star according to this utility function. Okay, across all the points, that it's going to be the expectation under the posterior of f of x given d, and we're going to examine all these points and give it 0 if it's less than F star, and we give it the value of how much improvement there is with F compared to F star. How much has it gone up? And actually the next one I think I'll show tweak minimisation, that's fine. If you take that expectation, and you know these parameters, you take that expectation, you can write it out. Okay? Integration by parts gives you that. So we actually have a tractable, what they would often call an acquisition function. Okay? So, on the red line here, this red line is that acquisition function. And what you notice, it has this, you know, positive impact or not on it when you do the expectation over the posterior of the Gaussian process. It also has these terms to do with the variances of these points. And what it's essentially doing is saying, and this is the argument between balancing a local v global type of strategy, it's saying, you know, yes, we certainly want things to be going up when we do it. That's exploitation. I know the maximum's going to be at least this big, but if you just keep doing that, then, you know, it's very local and you might be getting stuck. But if we have these extra terms that result from this, like these variances, these posterior predictive variances, it also suggests that, well, there is then a trade-off between going up and exploring spaces that are of high variance. That's the sort of argument for global optimization. Because, you know, and effectively, sorry, what you're doing then is maximizing this function. Okay? And you're doing that using pretty standard techniques most of the time. thing is, well, often you just don't even know that function in the first place, but you're getting realizations from it out of a computer experiment or something or other. But sometimes it's also just a very complicated function, and this is easy, right? This is a much more straightforward, this is an analytic object we got. We can get gradients and go and go up and get to the, you know, getting arguments of that function, in this case here, will then give a new point, and then you say, well, if that's the case, you know, we haven't observed things through here yet. Chuck one there, see what happens, and see how everything else tightens up. This bimodality, the claim then is that, you know, if this variance overwhelmed this piece of high, you know, higher value, then it's possible to be jumping across into this one. This bimodality, maybe you get around, but his paper seems to rest on that, I think. Anyway, it does seem to work pretty good, so I don't want to slam on too much. So, you know, generically, initialize some data. You can select an xn to get the, to maximise that. That was that last equation on the bottom screen. There's not many equations in this talk. Observe your next point, update your data. Do again, until at some point, you're satisfied that you've got a maximum. So, for this function, I'm actually doing it with a minimum, but that's all right. Put a negative in front of it. You know, you start off with these points, plot your expected improvement, choose that one, put a point there. Plot your expected improvements, choose that one, put a point there. Similarly, and you'll notice then these expected improvements are getting lower and lower and lower as you go through. And in fact, you can show actually at the point itself, so you wouldn't be selecting, you've already observed that, but the expected improvement is 0 at that point. You know, variance is 0, etc. So, optimise it again, and effectively you're 0 everywhere. Where's that cutoff? I don't know. Where's your tolerance in a Newton-Raphson step type idea? Okay. So it's actually a really cool idea, I think. I didn't do anything to my computer. So as I said, you know, they claim to be optimal. Now, well, so claimed, but there might be some really esoteric forms of, you know, bounded regret functions that maybe someone's done it for, but it's not obvious to me. But it's certainly designed to be global, and it's pretty good, actually, as long as you don't have a thumping great dimensional space on the function space itself. You can often optimise under a limited evaluation budget. Okay, so that's the same as just getting that surrogate in the first place. You get a pretty good approximation pretty fast without having to do full Monte Carlo runs, if you like, can also be applied to functions and processes with noise. And that's a handy thing. Some of the stuff breaks down in the sense of hard theory, because, you know, you're never then observing that signal, you're wanting to get the optimum of that signal. You're only observing that signal with noise. And some of the optimality criteria, for example, of expected improvement gets lost with that. It gets harder to define as you do it. And you don't need any of this stuff. So effectively, you know, did I put it up there before? Maybe not. Oh yeah, it's one of those sort of things, you know. It's like maybe doing integration via Monte Carlo. Sometimes uncertainty can be your friend. Okay, just simulate a bunch of stuff, take an average, that's an integral. Okay, so that's bringing us back to this point, which is back to drifters. You know, these guys, they hang out on boats and the operators do that and they drop them and they want to see, you know, the basic structure they had for us is like a box in the ocean. And they know they want to do some operation in there. Can you learn about that? But the box can be pretty big. Where would be good places to go and where would be good places to set the drifters, of which I'm not going to show you anything about, okay, because we haven't done it. We've just developed the theory, etc. I gave you warning. But we need a learning policy that's going to respect the drifter trajectory structure. Okay, so we've got a vector field now with surface currents. We have a vector field that's moving. We also, and when I say learning policy up there, I mean learning in the expected utility world. So we need probability distributions to talk about these. Okay. we want to be able to think about where those drifters go, because they'll be getting us extra information as they go out there, and avoids too much computational cost. I just put a shout out there. These guys, you know, this sort of gave us all a little bit of a heart attack about 6 months ago, and we suddenly went, oh man, these guys are, they're doing a slightly different model of the trajectories themselves, and then there's no notion of, but it's good work, so if people are interested, they're going much more directly to the physical dynamics and you know, OU, stochastic processes, errors and those sorts of things. But anyway, it's Wiggins is from Bristol, and these two are in the US somewhere. But there's no notion about if we drop a drifter, where do we do the next one? All right, so how do we construct something like that? Well, the Helmholtz decomposition that effectively breaks, you have a vector field and you deconstruct it into its, you know, curl-free and divergence-free components. Run these grad and rotation operators over it, and that's a representation of that vector field. Okay, so, you know, the potential there, you assume he's got no the potential there, you know, it's not going to have any, well, there's some independent direction, effectively velocity and going out, as we're just assuming that it's got no swirling action, or we've got swirling action but nothing pushing out or contracting in. Okay, put it in layman's terms. If the handy thing is, if we do that, we can put Gaussian process priors on those two, right, and construct a what we call here a K-Helm, which talks about, which is a Gaussian process kernel that is an approximation, if you like, of this sort of Lagrangian vector fields of fluids. That's what it comes down. It's quite new in the literature, this one. Lachlan did a lot to develop this stuff, actually. So, you know, you have that vector field, say, you know, you're putting in, that's the truth, you put in drifters, and as the drifters move about, then you get a new posterior, and you think, where do we drop the next ones, etc. So that's the basic notion. So what we do then is the next drifter deployment takes place at a location X star, and what we're effectively doing is getting a field approximation at that time from the drifter, okay? And that is from an estimate, GN's, that's a GP. We're getting an estimate of that based on the data we've already got by having this, you know, sample and average type idea. And the projection is just then this, you're projecting across the vector field, according to that field approximation with the usual type of, you know, numeric intervention with Euler discretizations, step numbers and all that sort of business. So that's the idea, that's what's happening on these ones, okay? And you're thinking, what happens as they move through the drifter? You'll notice, or maybe you don't, you notice at the moment there's nothing time dependent exactly. There's nothing time dependent, that's what I said, this isn't finished. There's nothing time dependent in the vector field, which of course the oceans will have. So that's a little extra level of, we're just pretending that there's some sort of time, we drop drifters on, it moves around, but actually we have a static, in the true sense of the word ocean, if you like. I know that feels a bit funny, we're trying to get a hand on it. This stuff actually went into NeurIPS, but that was previously in a workshop. Right, we talked about that. So, and, you know, then we construct some different utility functions. You could, all sorts of things. Expected information gain, which is essentially just like a Shannon, like entropy, okay? This one here, max variance, we're going to choose the point at which our latest model has the highest variance. In other words, can we reduce it by a lot when we plonk the next one in? And here we go, then we've got movie. You know, so it starts to circle around there, and then you're dropping other ones, etc. When they go outside the boxes, we kill it, because that's from an industry thing. They look at it and go, well, we're not interested out there, and if it goes out. So anyway, or you could have something like an integrated variance, where you're measuring, effectively that boils down to where you're measuring the latest model, which has the least total variance if we knew that point. guess he's sort of averaging over all these trajectories and going, where, if we had that, what, can we identify this? The answer is yes, we can. And we do all that sort of thing. And so you see these vector fields, we start to get better and better approximations of that, etc. Simulation stage, we'll forget, this is sort of stuff that went to NeurIPS, but what would happen if we didn't do this? We just went dropping them uniformly or something or other, okay? That's, and so you're breaking up into this grid sort of based on base 2 type things, and a whole heap of extra stuff. Wherever you see ballast in there, that's where we're considering the trajectory actually of it going forward. And by and large, they're encouraging. I won't give it much more than that. It was encouraging enough for a few machine learners and NeurIPS to go, yeah, okay, this is looking all right. And of course, then what we were thinking mainly about in Lancaster, I'm probably getting towards the end of that time there, what we're thinking mainly about in Lancaster is, of course, what happens when the ocean doesn't stand still for us. And so we've been starting to develop that. And effectively, and now there could be much better ideas than this for anyone who lives in GP world, but what we've done, we call this KT helm, and essentially, you've still got the Helmholtz Gaussian process prior on the spatial field, and if you think about the cube, in time, that spatial field in cube, it's kind of, it's what we call separable. You can just tack on the extra covariance matrix to it. It's a product, K time by K helm. And if you think about that, what you're doing to try and put into maybe layman's or people's terms that haven't dealt with this, what effectively you're doing is you've got dependency in space, and at each point you've got dependency in time, but you haven't got that one. Right? You haven't got it cutting through the space and the time at the same time. There's no explicit dependency in that. But they're much easier to work with and start to get a handle on. So that's effectively what we're up to now. So in that one, you chuck in a few drifters, see where they go, get a GP type regression with Helmholtz and all that sort of stuff, and with time dependent, generating them and in space and time, sample, simulate a bunch of them, identify here a spot, we just put utility, let's say it's maximum variance, that's your next spot you go to. I think. So now that's all still under a lot of work there. And you'll see here, you've also got this T floating around, you're going to get the Fs across space and time and all the rest of it, but it's doable and it's actually not too computationally heavy. We are actually, one way to speed that up, and I haven't put this up here, is that if you can represent the Gaussian process as a stochastic partial differential equation, it speeds things up well. Okay, and you'd be getting at the same thing. So just to iterate, this Helmholtz GP is definitely not an exact replication of this vector field for the fluid motion. It's an approximation. It's a probability distribution over it. And even more in sense of, I didn't put it up, but the K of time is what we call a turn function. So it's just a stochastic process in 1D. Okay? That has certain time series characteristics. Down below here, so 2025 plus, because we can get everything done, and ongoing work. It's actually probably not too far away, at least the first pass. There's going to have to be lots of, we can do better than that. That's probably, but again, you never know with these GPs and stuff, they can be pretty, like Bayesian optimization, you go, really? And then it works. You go, oh, okay, that's pretty good. So, my last point, actually, I will make, I didn't, and if it occurred to anyone previously, just thinking right back to the optimization problem. It turns out, certainly in practice, it doesn't so much matter if you choose this one instead. Say if you had some sort of gradient ascent type algorithm across this and you choose that one. It doesn't, it still updates this and you get your new function that's going to start to behave more and more neatly. So you might waste a bit of time, an extra couple of runs, but it's not the end of the day if you do choose a different maximum in there. That's it. As I said, I'm going to leave you hanging. I'm afraid we're just getting to the good stuff, but that's my career at the moment. I'm just at the edge of that good stuff. So, any questions? Yeah.
Splitting the field into two bits, one's gradient type, one's divergence.
Yep. Yep.
Because of the kind of thing you're studying, I would have expected the field to be mainly divergence free because that model is incompressible flow.
Yeah, it could be. There's certainly, yeah, it could well be.
With a qualification.
With a qualification.
Which is this is not, which we do actually have movement up and down.
Yeah, you got advection that comes up and down in the.
Coming in there, perhaps.
These guys will answer that sort of question. I'll jump up straight away and go, I'm not an oceanographer in fluid mechanics, but there's two guys here who are, if they're willing to. We can ask another question instead. We can talk about it. Yes, Carol.
So I'm not an oceanographer, but I published a paper on numerical method to solve surface flow on the Mediterranean Sea.
Yeah, okay.
So this is a relatively simple set of 2D equations,
Yep.
simplified Navier-Stokes in such a way. Should it not be used somewhere as a constraint on the stuff?
You could.
Because then maybe it
Yep.
would shrink,
Yeah,
right?
yeah. Tighten things up. Absolutely. Yeah, it's a
So-
good
so
suggestion.
it's not fully blown Navier-Stokes. It's
No.
much easier than that.
Yeah,
and,
that's
we
right.
actually have a very efficient numerical method to
Yeah, okay.
to solve. So that's one comment.
Can you send us the link to that paper?
Yeah.
Yeah.
And the second is this on this slide, the 17.
Oh, doesn't give me my slide numbers. Tell me when to stop.
It's 18, 17. Yeah.
Ah, yeah.
So,
Yeah.
the last one.
Yeah.
If from divine illumination you were given the gradients,
Yeah.
how much easier would it become?
Look, I don't know. I've never.
Because the thing
Yeah.
is that theoretically,
Yeah.
these things could be approximated by a neural network.
Absolutely.
The neural network
Yeah.
perhaps some kind of a pin constrained by these
Yeah.
equations I mentioned.
Yeah.
And then there may be a possibility to compute
And you got
gradients.
gradients. Yeah,
Yeah.
quite. So look, maybe there's. I mean, when I talked about GP stuff for surrogate models, it's not the only surrogate model. So lots of people use neural nets for that. So, and of course you do get gradients out of that, and maybe you can start to then think about whether, I mean, I presume you'd be doing that then on the original unknown function, right? You'd be operating on that space, so maybe you still wouldn't be sure whether you start to wobble up. You're not taking sort of, you know,
So the thing is that some people say that these gradients come for free, essentially.
in neural nets,
Yes.
if the computer program does it for you, yeah.
I mean,
Yeah.
but it's there.
Yeah,
right?
yeah,
So
yeah,
it's just a
often is.
matter of asking it to output it. It's
Absolutely.
not like more
No.
stuff.
Yeah. No, absolutely. Now, whether that would then, okay, and then if you want to use that to get an optimum, I presume then you're saying I want to do that using gradient-based sort of knowledge. Does that help? And maybe it would, but maybe also suffer them from the same problems that if I could actually get the gradients and I just use them to try and search. I don't know the answers, actually, to be honest. Well, what you wouldn't get necessarily, what you wouldn't get necessarily, just saying, all I'm going to do is use a neural net, is you wouldn't have that uncertainty that gives us that bonus to jump around globally and locally, but putting a posterior distribution over. If it's just a strict neural net, you're just fitting some manifolds or something. But, and I know Nick will be somewhat familiar with this stuff, and I'm looking at stuff with Mike, is how will you combine neural nets to speed up this process? And by that, I mean, if you go and look up things like amortized learning, there's been some papers coming out on that. They're essentially using neural nets to learn, to obtain statistical estimators and things like this. Right? So you just, anyway, but there's a whole heap of stuff that you could, because I think you guys have been doing stuff in the medical thing. Me and Mike have been looking at it a bit recently. Could we speed this process up down on this grid by using these neural nets? Essentially what you're doing is you have a model, you simulate from that model a gazillion times, right? Then you train a neural net over the loss function that you want to estimate your parameters with, okay? And because you can simulate a lot of times, neural nets love simulation, it loves data, it smashes it, right? And then your last part, so you get this estimator for it, you're just feeling essentially at that point to your neural net doing this over all these ones, and the law of large numbers to get this estimate. Say squared error loss, you get a posterior mean. And then the last data set you tack on is the data set you actually want, and you can update with that. So can we do that in this space that makes it handy? That's what we're looking at. But unfortunately, honours students are rather challenging problem perhaps for an honours student. But anyway, we'll see. So there is all sorts of ways these days. Neural nets is getting fed into, so statisticians like that, because the neural net's being used, and it's surprising, I don't know, a bit like days off, I don't know if there's theory that backs this up, but over a year of watching like this, all right, it seems to be pretty good. But what it does is, for statisticians, we love it because we still get the inferential take that we get from a statistical model, and we're using the bonuses of neural nets, purely like, for example, an MCMC algorithm to get the handle of what these things are. So that's what we've been, so all what neural nets on their own, or neural nets with the actual probability model, I think they're going to play a big part in the optimisation procedure, one way or the other, and the fact that you get gradients out. That's a really handy thing.
I mean, like, just nothing related to the physical scenario. Don't be afraid. So
I'm always afraid of you. If you
in our simulation, we have similar stuff. When we are running 40 bar, we have the observation impact kind of estimates, and we have similar kind of ideas how to optimize observation system to give you the best, basically, in a model. But it's made by the adjoint and going back and forth.
As in the adjoint matrix?
It's kind of like adjoint of the adjoint.
Yeah.
So you get the sensitivity of the system. And how you should observe to get kind of the biggest gain metrics.
Yeah.
So it's basically, optimization theory as well.
Yeah. There's a, I hope I made it's good, actually.
Just wondering about the drifters, basically.
Yeah.
Then you drop one,
Yeah.
it's going to observe your system and kind of minimize the problem.
Yeah.
But later on, it's not going to be useful because
No.
it's going to go somewhere where it's kind of like,
I
system
know.
is not going to learn anything.
I spent the first couple of years arguing with it.
If you take it off and put it on the, like for example, you have 10 drifters.
Yeah.
How to shuffle
Can you
them
reallocate
one
them?
time
Yeah.
and get the best of that.
Yeah. Yeah, that would be, you could think about that as a strategy, absolutely. And for the first couple of years, whenever I was watching them drop off these drifters at certain spots they'd be interested in, I was like, why? They go away. They were here for an hour and now they've...
If I may, if you have reasons to believe that the model of the currents is actually good,
Yeah.
then,
Well, that's another...
then you don't need that many drifters to calibrate it, right?
Absolutely, yeah, if that's the case, absolutely. It's not the way that people put it with us, so we're not dealing with that. But yes, I got your point. We have a lot of discussions, I think, ahead of us with how to think about measurement devices, etc., with oceans and all the rest of it. But yeah, if you've got a really good model, who cares? Yeah.
Thanks, Ed. That's really nice.
Thank you.
Like the Helmholtz kernel stuff.
It's pretty new. It's like, certainly the last few years, maybe a bit older than that. And it comes about because, okay, so you decompose that, as we said, into a sort of a curl-free and a divergence-free components, and then you're putting those operators on them, which are differential equations, right, partial PDF. And the handy thing about it is, I'm sure you know this, the derivative of a GP is a GP. So it just falls straight out. Yeah, and that's the very handy thing about it. So,
My question is actually going to be more about making your life more complicated.
Yeah.
Now, I imagine somebody who wants to put out drifters doesn't want to do one and then go to the other side of the ocean.
No.
Whilst waiting for you to run model, they want to do a batch, close together in a series. Is that easy to solve just with trying out the utility function?
No, and we've been doing that. So you drop a batch and then think where you get. So they're not necessarily doing one at a time. And the other one here that you might have spotted that I glazed over is that you're really living now in a non-myopic world. Right? A lot of Bayes op stuff is myopic. Take an observation. Where do I put the next? Whereas once you start getting trajectories going, and then you've got to then for these things to be optimal in some sense, you've got to satisfy those Bellman equations, which essentially says the whole optimality choice procedure has to follow all the way through. So that there's heaps to be done in this space. It's quite good, and it has a mix of the physics side. It's got a mix of applications. It's got a mix of and a big question I had